Okay, I think it seems like we're all here. Thank you everybody for joining this webinar about thermal treatment and challenges and solutions. And during the next half hour, I will present to you some of the lessons we have learned over the years and some of the challenges we are facing. First of all, I'm Steffen Griepke. I'm the principal engineer and technical director at TerraTherm. I've been with the company since 2008, and my main work tasks are subsurface design and technical direction on our projects. So I'm leading up our subsurface design group and also help out as the technical director for quite a bit of our projects. And on the agenda for today, we've selected 4 main topics, basically all of them related to some of the challenges we are facing when we design our projects. First of them is, first I'll talk a little about groundwater flow and how it impacts our operations. Second, I will talk about the condensation zones and why it's important to know if they are there and try to prevent them. Third, I'll talk a little about how we approach high mass sites, and a little bit related to that, also some of the corrosion issues we have seen in the past and how we try to mitigate them. So after the main presentation, that probably takes roughly half an hour, we will have a Q&A session. And feel free to ask some questions. I'll provide a little more information about that in a little bit. But also, before you log off, you have an option to complete our webinar survey, and we definitely would appreciate if you could do that. First of all, to provide input on this specific webinar, but also maybe provide some topics that you would like us to look at in the near future on any of the additional webinars that we will be looking at moving forward. As a part of the webinar survey, you get an option to request a copy of the slide deck if that's what you want. So on your screen right now, you should have a little box, a little panel, and in that panel, it looks like shown on this screen. Here you're able to ask a question. You can ask a question anytime. And then after the presentation, we'll try to attack those questions. You can also raise your hand, as it's called. It's the bottom up here. If you do that, we can unmute you, and you can ask a question verbally if you would rather do so. So I think that was the more practical pieces of information, so let's get started. Before we start, I would like to just talk a little about conceptual site models and why it matters a lot for all thermal vendors that the client or consultant has fully nailed down the conceptual site model. So of course, when we design a thermal project, we can only base it on the information we provide. So first of all, the geology at the site and the hydrogeology is of a special interest to us, but of course also topics like site infrastructure. You know, is there a building above the area that we are trying to treat? Are there any major pipes and lines and internet connections or whatever in the treatment area? Because that probably means that we have to take that into account when we design our systems. Of course, the contaminant of concern, the COCs, what are we trying to treat? What are the treatment goals? And of course, very important as well, where exactly, how is the site delineated? So especially the delineation of the site is important because it pretty much costs the same for us to treat a cubic yard of clean soil compared to a cubic yard of highly contaminated soil. So as closer we as a team, or especially the consultant and the client can nail down the source zone, the better and more cost competitive can thermal methods be. And then of course, yeah, the extraction strategy is based on the hydrogeology at the site and what kind of material what kind of geology we're treating as well. So that plays into the total picture as well. So once we understand the conceptual site model, then the first step for us will always be to run our thermal models. So at TerraTherm, we run the heating. We have a numerical model that we always run. We call it the numerical heating simulation model. The model is used, first of all, to understand the duration and energy needed to heat the site to the desired target temperature. And one of the outputs are shown here in this upper left corner. It basically shows an example output from our numerical model with the temperatures here on the y-axis and then the duration of the project on the x-axis. And for each layer, we basically divide that site into different layers. And for each layer, we look at the energy bounds, look at the energy injected, the energy extracted, and calculate and try to predict the heat up profile for each layer. And of course, the goal at 100-degree sites that we normally are facing is to get up to temperature and maintain the temperature for a certain period of time and allow the contaminants to be stripped out of the subsurface. So, and the reason why we have a couple of temperature charts here that are not reaching the 100 degrees is that our model also takes into account that there are layers below the treatment zone that don't entirely get up to temperature, but we still need to account for the energy exchanged with the areas surrounding, above, and below the target treatment zone. Additionally, we have a couple of other models that we sometimes utilize. We have a cooling simulation model that we can use if people or if the client is interested in knowing exactly how the site cooled down. So after we leave the site, we leave it at probably at 95 degrees Celsius, or at least very close to the boiling point. We typically turn off our vapor extraction system when no fugitive emissions are created in situ. But then it can take up to at least months, but in at certain sites up to years before the site is fully down to ambient temperature again. So we have a model that can help us predict that. And we also have a model that predicts the heat spreading down gradient if needed. So when we stop our extraction at the site, and allow ambient groundwater to flow back in, this model can predict how is basically the plume of hot water leaving the now hopefully fully clean site. How is that one migrating down gradient? And typically that can actually benefit the plume outside of the source zone, since the hot water typically will enhance the natural biodegradation due to the increased temperatures. So part of the outputs from our numerical model is, of course, a base case scenario, and shown here to the left, where again on the y-axis we have the treatment depth, and on the x-axis we have the temperature. The red dotted line down here is the bottom of the treatment zone in this example, and what ultimately we want to achieve is to get over time a uniform heating, and each of these lines represents a time step during operation. So over time we want to get up to temperature, at least achieve a very uniform heating within the treatment zone. And then of course below, it doesn't matter as much if we don't get fully up to temperature. However, as you see here in the middle picture, at certain sites, groundwater flow and heat losses at the bottom can prevent us from getting up to the temperatures. And part of the modeling and the sensitivity studies is, of course, to understand exactly, based on this, the certainty of our input parameters, where we should be extra careful and where we should add more contingency to the design. And on the last one, basically that's the same, pretty much the same issue, that sometimes if we have extensive heat losses at the surface, the same happens at the surface. So we get to a point where the temperatures don't increase anymore, and basically the heat losses are too great to overcome if for some reason the vapor cap was designed wrong. So, and just looking, taking one step back, the water the water content and the water flow is a very special interest for us, and just a little, behind a napkin calculation shows us that if we want to heat a totally dry cubic meter of soil, it takes 43 kilowatt hours just to get that cubic meter up to 100 degrees. However, as the saturation increases, this energy requirement almost doubles when we're looking at a fully saturated cubic meter of soil, and that's basically just because the heat it takes to heat up 1 unit of water is 4 times what it takes to heat 1 unit of soil. So, and we not only need to heat the soil or this cubic meter of soil up to temperature, we also need to evaporate a part of or a fraction of the pore water, since evaporating the pore water is what creates the steam drive through the site and basically flushes all the pores and serves as a media for the contaminants to get out of the soil. So typically, TerraTherm, we aim for evaporating between 20 and 40% of the pore water. By doing so, we flush each pore on average between 300 and 600 times with steam, and that's basically what helps us reach the remediation goals at our sites. This slide shows basically a plan view of a model we ran for a site. So the red colors are simulating, the boiling point temperature, while the more yellow the colors gets, the colder the cell or the block in the model is. So if we look at the one to the left, simulating a site where we don't have any groundwater flow, the site heats up and very uniformly, and we have a nice hot site in all areas. But as we apply more and more water, here in the middle one, we apply 5 GPM of water, or corresponding to 1.1 cubic meter per hour. We see that the perimeter on the up-gradient edge starts cooling down, and if we don't have hydraulic control, we actually start creating a plume on the down-gradient edge as well, which at this point in the operations where we don't have fully removed all the contaminants is not good, of course, because that means that contaminants are leaving the sites. And the more water we add, the more obvious this phenomenon is. So basically, if we don't have groundwater flow, fully control of the groundwater flow, that will affect the duration of the project and, of course, the power usage. And in certain instances, it can even prevent us from getting to the end goal without having to add additional features to the site. And this is actually exactly what happened at a site we recently treated in upstate New York. The couple of months into operation, we saw that the temperatures started to not decrease, but they started to level out below the boiling point. And after going out there and conducting some sludge tests, we found that the water was flowing 30 times faster than expected and predicted by the site conceptual model through the site. And as a result, the site didn't heat as predicted. So for this particular site, we had to come in and install a sheet pile wall on the up-gradient edge, basically to stop the water flow, and to catch up on some of the time that we have wasted. We ended up installing more heaters and adding extra heating capacity to be able to reach the goals. So I think this example just shows that it's very important, even during operation, of course, to keep a close eye on the heat up compared to what we modeled, and take actions if the two things doesn't agree. not only natural or groundwater flowing under natural gradients can impact our heat up, also the well designs can impact it. And we have actually learned that the hard way on one of our sites. At the specific site, we had to go with what we call co-located vapor extraction. So our heat element was installed in a borehole, and right next to it we installed a vapor extraction well. And for this particular site, it was installed all the way to the bottom, so along the heater element. At this site, the groundwater table was 15 feet below grade. And basically what ended up happening was that the steam generated deep at the site and next to the heater ended up pushing hot water out of the formation, basically like a airlift pump. You can compare it to an airlift pump. And I just returned from a vacation in Europe and found that my family had a coffee maker that actually very nice describes this phenomenon. So this is the coffee maker. We have down here there's a heater element, and since this pipe allows the water to migrate from basically from this reservoir and up, when the steam is generated deep at the site, it flows out through the pipe, but entrains a bunch of water. So this airlift phenomenon is definitely something that we want and need to avoid. And this is not only the case when we have co-located extraction. We have also seen it at other sites where steam is generated deep at the site, and a confining layer like clay, for instance, above a sand layer is preventing the steam from flowing upwards and get captured. So instead, the steam may find its way into the extraction wells and entrain water as it flushes on geysers. Pretty much, you can compare it to a geyser. Geysers up the well and into the vapor treatment system. And of course, if that's the case, we end up removing a bunch of hot water. And we've seen wells like this produce up to several gallons per minute of water. And since that is, typically right around the boiling point, it's a lot of energy that is removed from the site and thereby is not working as anticipated to basically stay in the ground and remediate the site. So one of the fixes is, of course, to shorten the extraction screen and make sure that it's only screened up in the vapor zone, such that we are not entraining that same amount of water. Okay, once the water is under control, then we need to focus on potential condensation zones as well. So the two pictures here shows our typical vapor cap construction. So while heat mobilized contaminants, they, cold zone also drop them back out if the concentrations are high. So understanding where the condensation zones are is definitely key, and the first place, of course, is at the surface where we have excessive heat losses. So typically, especially when we're treating to the surface, we always install a vapor cover, and the vapor cover serves three different purposes. First of all, it prevents rainwater infiltration. As we previously learned, all water is challenging for all thermal methods, and so by constructing a waterproof layer on top of our zones, we at least have control over the rainwater during operation. Also, the cover allows for pneumatic control and allows us to add a good vacuum below the vapor cover and thereby capture the steam and the contaminants volatilized by the thermal operations. And probably third and probably most important, it also helps insulating the surface and reduce the heat losses. And actually, just looking at the numbers, if we're looking at a site without a vapor cover, the heat losses per square meter can be as high as 2,000 watts per square meters. and compared to a good insulated site where the heat losses are between 30 and 50 watts per square meter. So the vapor cover can, a properly insulated vapor cover can decrease the heat losses by up to a factor of 40 to 70 times. And to the left in this picture, this actually shows an example from a test we did in San Francisco on different covers, and this is pretty much what we want to see. So the blue line here represents the temperature of the vapor cover at the very bottom, and for this particular time series, the vapor cover temperature was roughly 80 degrees. And what's more important is that the top, basically the surface of the vapor cover, was a lot less than that. In this case, you know, right around 24 degrees Celsius and 75 degrees Fahrenheit. And since the ambient temperature during the project was in the order of 65 Fahrenheit and 18 degrees Celsius, and basically the temperature difference between the cover and the ambient air is what drives the heat flux, then this is a very good situation, because it shows that we are losing, or the heat losses are limited to you know, a fraction of what it would have been if the surface was 100 degrees Celsius hot. So another way to look at the condensation issue is to just look at the physical properties. For TCE, the saturated vapor concentration is 700,000 ppm at 80 degrees Celsius. So we can assume that if at a high mass TCE site, we will probably have concentrations close to that in the pore spaces. So on the other side, if we look at the chemical properties, if we just decrease the temperature by 20 degrees Celsius down to 60 degrees Celsius, that same saturated vapor concentration is only 400,000 ppm. So in other words, if a saturated TCE vapor mass is allowed to migrate out in a colder area, then dropping out TCE NAPL is almost impossible to avoid. So, and this is another good example of that. This is from a site we had in, we operated in Tennessee, and due to a damaged vapor cover right next to an extraction well, we saw that condensate was accumulated. It's a little hard to see, but the black area right here is actually NAPL that is condensing out right next to the vapor extraction well. And of course, that's not desirable at any thermal site. So some of the tools we have in the toolbox to investigate this and address issues like this is, of course, infrared thermal imaging. And here are a couple of examples. Down here shows a vapor cover with you can actually see the manifold piping here and the treatment system here in the background. But you'll see that, you know, the yellow and red colors shows the areas of the cap that has the highest heat losses, and if needed, that's where we would start adding more insulation during operation if we found it to be a problem. And does this really happen in reality? Yes, it does, and we have actually seen it. So we have seen shallow condensation of mass, and thereby, you know, up concentration of mass and right close to the surface. And the example I brought today is from a site in California. We treated the site using a combination of thermoconductive heating in a top clay layer, and then we added steam at the bottom in a sandy aquifer. And what we saw at this site after a couple of months of operation was that the temperature just below the vapor cover, so the blue line right here represents the temperature just below the vapor cover. We saw that it basically leveled out just around 70 degrees Celsius. So to see if that was a problem, we went in and collected shallow samples and found that right on below the cap we had 2,000 milligrams per kilograms of contaminants condensed out. And of course we knew that the only solution here was to insulate the cover even more. We actually had a good air entering cover on this particular site, but it was not perfectly waterproof, so rainwater infiltrated it and brought down the insulation value. So instead we went back in and added more insulation, and 6 weeks after the extra insulation was added, we went back in, collected more samples, and found that since the temperature after the insulation was added increased to up above the boiling point, actually, the soil samples also showed that we were way below the treatment goal for this particular site, and we found concentrations right around 5 milligrams per kilograms. So the next topic is, how to deal with large chemical masses during thermal remedies. And since all thermal technologies, whether it's ER8, thermal conductive heating, or steam enhanced extraction, definitely is a source zone technology, we typically expect high mass, and I'm sure our competitors do as well. And for us, it's not unusual that we, during peak operations, remove between 2,000 and 3,000 kilograms per day, or corresponding to anywhere between 5,000 and 7,000 pounds. So, of course, that requires us to be able to treat all that mass at the surface. And the two most common systems we use is the relatively simple GAC system, granular activated carbon system. We of course prefer that because the carbon system is simple to operate, and it has generally a good regulatory acceptance. The absolute downside is that if the mass estimate is off and we end up removing twice the mass and predicted, then the cost of running a GAC system scales with the mass recovered. So on higher mass sites, we typically utilize the thermal oxidation. The good thing about a thermal oxidizer is that it will chew through the mass, and no matter how much mass there are, to a certain limit, of course, the cost of operating the thermal oxidizer is almost the same. And actually, the BTU, or the energy value in the mass recovered from the subsurface, actually sometimes helps saving on the supplemental fuel, typically natural gas, that we have to add to the oxidizer to maintain the temperature in the oxidizer beds. The downside of a thermal oxidizer is that it requires highly skilled operators to keep it running, and the capital upfront cost is of course higher as well. And additionally, especially when we are treating chlorinated sites, the thermal oxidizer may have to be followed by a scrubber step, basically to get rid of the acids generated when chlorinated solvents are burned at high temperature. So since this is an example from a site in Connecticut that we recently treated, for this particular site we predicted the peak mass loading, if we were to treat it in one shot, to be 16,000 pounds per day. And of course that requires quite a thermal oxidizer to be able to handle that. So instead, for this particular site, we decided to phase the thermal remedy, and in reality that meant that we divided the site up into two different phases and started phase 2 roughly 2 months after phase 1. And the entire idea with doing this was to try to even out the mass loading on our treatment system and thereby bring down the sizing, because ultimately, if the treatment system cannot handle the mass extracted from the subsurface, then we only have a couple of buttons to push, and one of them is basically to slow down the heating and allow more time for the contaminants to come out, and that adds cost to the total project, since operating thermal systems of course has a cost tag associated per operational day. So instead of one big mass removal curve here, we predicted or was hoping to see two individual peaks, and so the resulting peak at our treatment system would be evened out quite a bit. And this is just a well field map showing exactly how we divided the site up, and we made sure that we tried to divide the site up such that we had the same amount of mass in each of the two areas. And this is an aerial photo of the site, where you see the treatment system located down here, and then the thermal well field out here. And of course you can't see the two phases, but we had phase 1 up in this area and phase 2 down in this area. And in reality, what we saw during operation was that we ended up removing 500,000 pounds at this particular site, or corresponding to 227,000 kilograms. And while it's not obvious on the cumulative mass graph here, we have mass up on the y-axis and duration out on the x-axis. It's not obvious here on the cumulative chart that we had two separate mass peaks. However, if we look at the mass removal curve, and actually we had a thermal oxidizer shut down in this period, so that should be ignored. But if we look at the mass removal rates during operation, we have at least it trends like, we have two different and separate mass peaks. And as you can see out here, our peak was up around 7,000 pounds per day, but typically down around 5,000 pounds per day during peak operations. Also, all that mass sometimes leads to corrosion of our systems, and what we have learned is that we should avoid any kind of condensation in our systems if all possible. So one option is to basically keep the well field vapors heated all the way to the thermal oxidizer. And typically when we are dealing with corrosion issues, it's at our high mass sites where we utilize the thermal oxidizer anyway. So one option is to basically use insertion heaters to keep the mass or the vapors above the condensation point all the way through this thermal oxidizer. If not, something like this could happen. This is a picture from taking of one of our thermal oxidizers, where a damaged insulation in one of the beds basically led to heat losses in that particular area, and after that vapors condensed out, and acids basically corroded big chunks of the oxidizer. And this is of course especially an issue on fluorinated sites where the either in situ combustion, or not combustion, but heat up of the chemicals, or within the oxidizer, that combustion generates HCl, or hydrochloric acids. It is also a problem if we are treating fluorinated compounds, like since the byproduct there would be hydrofluoric acids, which is 30 times stronger acid than hydrochloric, so very, very aggressive. So on those particular sites, we try to avoid extraction near the heaters if possible. Then the soil itself acts like a buffer to some of those acids, and worst case, we end up adding acid neutralization systems within our treatment system, and I have an example of that in a little bit. And of course, select the right materials. Sometimes it's more cost-effective just to realize that we will have corrosion, and then just upgrade the piping to a higher schedule and thicker material thickness. And and other circumstances, upgrading to stainless steel or even better steel than that is also an option. So this picture actually shows an example of how we sometimes measure the PID in our influent system, and then if required, if the did I say PID? I meant pH. If the pH is low, then we are adding caustic to the stream right before the treatment system, and thereby trying to neutralize the acids before they even enter the treatment system. So just a brief summary. Rule number one, we gotta take groundwater flow into account and at least understand how it flows across the site, and plan accordingly. Either install a sheet pile wall if it's warranted, or lower the gradient across the site by installing upgrading groundwater pumping wells. Another thing we need to focus on is to avoid condensation, and especially shallow condensation is a problem for us, and by basically installing a good vapor cover. And third, for each specific site, we need to focus on the vapor treatment system and select the best option. And typically, TerraTherm utilizes oxidation system if the mass is high. And on top of that, we need to address any corrosion control that is needed, such that we can get through the project without damaging our systems. I think that completes my presentation. So if anybody have any questions, feel free to ask them now, and then I will try to address them right away.